We present our WACV 2026 paper, Robust Synchronous Regression via Geometrically Consistent Global Descriptors. In this paper, we tackle the visual localization task where we are given a query image and must find the 6 degree of freedom camera pose for this image with respect to the map. We focus on solving the visual localization task with synchronous regression. Synchronous regression models predict a 3D coordinate for each of the local descriptors from the query image. Together with the pixel coordinates of the local descriptors, we obtain 2D 3D matches and are able to solve for the position and orientation of the query image using the PNP solver. Synchronous regression models generally have lower accuracy than other methods for large scenes because they are sensitive to descriptor variation and suffer from perceptualizing. However, they have lower memory requirements and lower query time. Existing methods have been using location context to combat perceptual aliasing in synchronous regression models. In-glaze off-the-shelf global descriptors have been used. However, descriptor inconsistency can destabilize the training process. ASCOR proposed to use the embeddings from the curve visibility graph from the node-to-web formulation. However, the location context is disconnected from the image appearance. Therefore, rich visual cues are ignored, and noisy graph edges may lead to incorrect global descriptors. Our motivation is to find a location context that is consistent with both the visual appearance and the geometric structure of the curve visibility graph. With this objective, we desire a system to capture the location context that is consistent with the image appearance. First, we use DDoD, a state-of-the-art local descriptors for fine-grained geometry. Second, we use DynoV2 to capture the global visual context of the image. Third, we use a neural aggregator to aggregate the DynoV2 features into a global descriptor. Finally, we concatenate the global descriptor with the local descriptors to produce 3D prediction with the regression model. To train this aggregator, we modified the generalized contrastive loss with a more stable distance function. Here in this loss, Gi and Gj are the global descriptors produced by the aggregator from two random images. And size is the overlapping score, and the margin tau controlling how far apart these similar pairs should be. To construct a batch, we prepare three different sets of the same size. In the first set, we sample random positive pairs with overlapping score of more than 50%. In the second set, we sample soft negative pairs with overlapping score between 25 and 50%. Finally, in the last set, we sample hard negative pairs with overlapping scores of 0%. Here we show our descriptor quality compared to the graph embeddings of our score. For each reference image, we find the top k closest images using the global descriptors and plot the median translation error. Here we plot our score results in blue, our results in green, and the graph truth results in red. In the y-axis, the lower is the better. We can see that our descriptors have consistently lower errors on all of the maps. Here we show our quantitative results on the Aachen Day-and-Night dataset. On the y-axis, we plot the average accuracies and the memory consumption in log scale on the x-axis. Ideally, we want to be in the top left corner of this plot. In this dataset, we outperform our score by 2.2% with only 6 megabytes extra. We also evaluate our method on an indoor map. Here we show the same plot with accuracy and memory consumption. We again outperform our score by 2.5% and with 7 megabytes extra. For the ablation studies, we show that using a good buffer sampler strategy improves the accuracy by 5.1%. And replacing NetVLAD with Salad at test time improves another 1% in accuracy. Finally, using our modified generalized contrastive loss improves another 1% compared to the original loss. In conclusion, we introduce a neural aggregator for geometrically consistent global descriptors. Our aggregator, when integrated into existing synchronous regression models, improves 2.2 and 2.5% in accuracy for outdoor and indoor maps with only 7 megabytes extra. Thank you for listening.